Hi everyone, I'm Mohammad Khajanejad, and I'm going to talk about my joint work with Fatima Shaib and Professor Young on state estimation via indirect polytopic set computation for nonlinear discrete time systems. So I'm sure you all agree that state estimation is important in a lot of applications such as feedback control, fault detection, robotics, and power system. In this work, we are considering state estimation where the uncertainties are characterized as sets and particularly as polytopic sets. So polytopes have two famous representation, V representation, where we represent a polytope as a convex combination of vertices, the H representation, where a polytope is represented by applying hyperplanes. There are two more recent indirect representation of polytopes, zonotope bundles and constrained zonotopes. So any polytope is shown to be equivalently represented as an intersection of zonotope. And a zonotope is a fine transformation of a hyper box or a unit hyperbox or interval. Also, it is shown in the literature that any polytope can be represented by a constrained zonotope. And a constrained zonotope is simply a zonotope which is constrained by a fine constraint. So given this, it is shown in the literature that for linear systems with polytopic initial uncertainty sets, we can theoretically obtain tight enclosures for propagation of the polytopes under linear functions. However, it is computationally it is very extensive. So people, even for linear systems, so people have considered simpler initial uncertainty sets such as intervals, parallelotopes, and zonotopes. However, because of structural limitations of such sets, the results can be conservative. Hence, more recently, zonotope bundles and constrained zonotopes have gained increased attention, and specifically, very recently, constrained zonotopes have been used in the works of Regal et al. For nonlinear discrete time systems with linear and nonlinear observations. So in this work, we consider discrete time nonlinear constraint systems with nonlinear observations, where X is state, the augmentation of state and uncertainty W is Z, and this W, it can be any exogenous uncertain input, such as bounded process disturbance or noise and bounded system uncertainties. This YK is the set of constraints or observation. Both nonlinear functions are assumed to be local Lipschitz with bounded Jacobians. And all the uncertainty sets are assumed to be polytopes or equivalently constrained zonotopes or zonotope bundles. Okay, given this setting, we're interested in solving two problems. First is propagation. So at each time step, given an initial polytope, we want to propagate this polytope through the nonlinear function f. So we know that the true image set can be a nonlinear, a non-convex Weir set. So we are interested in finding a polytopic enclosure to this image set. Moreover, we want to refine that image set and find an intersection of the propagated set, which if the observation function is applied on, then it falls within the set of constraint or observation, which we call this problem the update problem, or the generalized intersection of the propagated set and the set of constraint through the nonlinear observation function. Okay, so we use a tool for this task, and that is a mixed monotone decomposition of functions. We showed in some previous work that given a local Lipschitz function f on an interval domain with bounded Jacobians, we can decompose f into two components, a Jacobian sign stable function g and a linear mapping which is characterized by a matrix H. So a Jacobian sign stable function is a function which is Jacobian, doesn't change sign in each dimension, so is monotonically increasing or decreasing in each dimension through its domain. So by choosing proper H in different ways, we can find a family of decompositions in this way. And for each decomposition, we get a Jacobian sign stable function G, which we can tightly bound from below and above. Okay, so with this tool, the main idea of this work is to transform from the state of from the state space to the space of generators. Generators are generators live in some intervals or boxes. So by transforming from the space of states to the space of generators, then we see that our polytopic uncertainty sets will transform into intervals. And then we can use our mixed monotone decomposition techniques to bound our functions in this new space, since everything is in the form of intervals in this new space. Okay, so with this idea, if we want to do propagation with the initial zonotope bundles, we transform to the space of generators, and then we do our mixed monotone decomposition on our function f into two components g and with use of a family of matrices, these HSs, and then we bound this Jacobian sign stable function, and we get a bundle of zonotopes. And we get a bundle of them because we can do this decomposition with several H matrices. So we get several zonotopes as enclosures of f of z. We take the intersection of all of them and we get a bundle of zonotopes. Similarly, if we use constrained zonotopes as the initial sets, similar steps can be done, with the slight difference that in the when we go to the space of generators, we have a linear or a fine constraint on the generators as well. And so it is shown that this also can be transformed into an interval. So everything is in the form of interval, and we can do the same thing for constraint zonotopes. For the update, when we assume that the propagated set and the set of constraints are zonotope bundles, we can do the same transformation to the space of generators now for the observation function. And then we can do mixed monotone decomposition and Jacobian sign stable bounding for the observation function. And by combination of these steps 1 and 2, we get constraint zonotope here. Okay, and then same thing can be done by using constraint zonotopes, and again by transforming the constraints into interval as I mentioned before. So conclusively, if we have polytopes as our uncertainty sets and local Lipschitz function both for vector fields and observation function with bounded Jacobians, we can derive enclosures for f of z in the form of zonotope bundles and constraint zonotopes. And as a conclusion, we can take the intersection of both. And also we can solve the generalized intersection function, the generalized intersection problem, and find enclosures to that, both in the form of zonotope bundles and constraint zonotopes, and take the intersection of Okay, we applied our approach along with some benchmark approaches on an example in this work. So this RSR, first of all, this first example is an example with a linear observation function. This RSR is an approach that uses mean value theorem for bounding. DRSR is a modification of that using our decomposition function for bounding. These DZB and DCZs are the methods that I just described, and this combination is a combination of all methods via intersection. So we can see that the sampled true sets of the trajectory can be nicely bounded with this combination, and this is a good and significant improvement to the existing approaches. And also we can apply our method to the unicycle system with the nonlinear observation function. And we can see that all the approaches return quite similar polytopes as the enclosures of the state trajectory sets. Okay, so we proposed a novel polytope valued state estimation approach for nonlinear systems with nonlinear observations. We considered indirect polytopic representations in the form of constrained zonotope and zonotope bundles. We leveraged transformation to the space of generators. We applied mixed monotone decomposition and Jacobian sign stable bounding. And in future, we are interested in doing direct polytopic estimation when we use V representation and H representation of the polytopes. We like to do a state and input estimation using polytopes, and we want to do polytopic state estimation for hybrid systems. Here is a list of some of the references that are used in this work, and by this I'm going to thank you all very much, and I will be happy to take any questions you may have.